Welcome to This Explainer. Have you ever wondered how big tech companies sort through absolute mountains of data in the blink of an eye? Like how your email provider knows exactly which messages to just toss into the spam folder? Or how a medical imaging device can actually pinpoint a disease from a simple scan? Well, it all comes down to a fascinating branch of machine learning called classification. Today, we're going to unlock the anatomy of this ultimate sorting machine. We'll demystify exactly how these algorithms learn to categorize information, literally turning absolute chaos into structured, actionable insights. Here's our roadmap for today. First, welcome to classification. Second, the math behind the node. Third, the cost of being wrong. And finally, learning from labeled data. Let's jump right in. Welcome to classification, the ultimate sorting machine. So to frame this whole concept, I want to pose a pretty fundamental question. How does a computer actually know the difference between a cat and a dog? I mean, to you and me, it's incredibly obvious, right? But to a computer, an image is really just a massive grid of pixels and raw numbers. It doesn't look at a picture and automatically see fur or ears. It has to be taught to identify specific features, things like edges, textures, and shapes from the raw data. And it has to do this without being explicitly programmed with a rule for every single dog breed out there. Basically, classification is a supervised machine learning technique that's used to predict labels or categories from input data. Crucially, I really want you to notice the phrase labeled datasets. Because classification is supervised, it relies entirely on an answer key. We show the model thousands of images that are already labeled as cat or dog, and it actually learns the underlying patterns connecting those pixel features to the correct class. Now, there are two main flavors of this that we need to understand. First up is binary classification. This is the simplest type, where the data is divided into just two possible categories. It's a straight-up yes or no question. Think of your inbox. An email is either spam or not spam, or in healthcare, predicting whether a patient has a certain disease or they don't. Second, we have multi-class classification. This is for when your data needs to be divided into more than two categories. The model analyzes the features and selects the single best class, like looking at an animal and deciding, okay, is this a cat, a dog, or a bird? Section 2, the math behind the node, opening the hood. Okay, let's dive into this math, and to do that, let's actually look at the finish line first. Imagine a neural network ending in what's called a softmax activation function. When the data flows through the entire network and finally hits that output layer, softmax does something kind of magical for multi-class problems. It takes all the raw calculated numbers and squashes them into clear probabilities between 0 and 1. So if we feed it an image, the network outputs a specific probability for cat, dog, monkey, or horse. Whichever class gets the probability closest to 1 wins. But you might be wondering, how do we generate those raw numbers before they get turned into neat percentages? Well, that happens inside the foundational computational unit of the network called a node, using a really fundamental equation. Let's break it down simply. Step 1. We take the inputs, let's just call them X, and multiply them by their corresponding weights, or W. You can think of weights as knobs of importance. If a specific pixel represents a pointy ear, the network is going to turn up the weight on that input. Step 2, we add the bias, or B. The bias is basically a baseline threshold that helps shift the result. So we sum up all the weights times the inputs and add that bias. Step 3, we pass that final number through an activation function, labeled as F. The activation function is the ultimate decision maker here. It decides if the node should fire and pass its signal on to the next layer, which introduces the nonlinearity that lets the network learn really complex patterns. And here's a crazy fact for you. In modern AI, a single model might literally have billions of these tiny math equations firing all at once. Section 3, the cost of being wrong, the scoreboard. Now, early on in training, the model's weights are completely random, so it's absolutely going to guess incorrectly a lot. We need a mathematical mechanism to track all those errors. Enter the loss function, which is also known as a cost function. This is a mathematical measure of the difference between the model's predicted output and the actual target values. Think of the loss function as the ultimate scoreboard, but it's totally counterintuitive. Unlike a normal video game where you want a high score, in machine learning, you want a score of exactly 0. The loss function tracks exactly how wrong the model is during its training. The whole aim is to minimize this cost, so the predictions get closer and closer to the actual results. Picture the data flowing like this. During forward propagation, data points, labeled x1, x2, x3, flow from left to right, passing straight through the hidden layers. They get multiplied by weights, biases are added, and activation functions fire. Finally, the network spits out a predicted value called y hat. Right at that finish line, it hits the loss function. This scoreboard compares the predicted y hat to the true target y and calculates the total error. Depending on the specific task, we actually use different scoreboards. For binary classification, like our spam or not spam example earlier, we use a specific function called binary cross-entropy. I know the formula looks like a massive wall of math, but seriously, don't let it intimidate you. The crucial takeaway here is this. It simply measures the gap between the predicted probability and the true labeled answer, which is always either a 0 or a 1. If the true label is 1 and the model predicted 0.99, the penalty is tiny. But if the model confidently predicted 0.01, no way, the penalty is massive. It severely punishes the model for being confidently wrong. Section 4, Learning from Labeled Data, the climax of learning. Okay, so we have the math, we have the scoreboard, but how does the actual true learning happen? It happens through a continuous 4-step iterative learning loop. Step 1, forward propagation. The data passes through the network to make a prediction. Step 2, error calculation. The loss function acts as the scoreboard to see exactly how wrong that prediction was. Then comes the magic. Step 3, backpropagation. The network literally takes that error and propagates it backward through the entire network, layer by layer. It uses calculus to figure out exactly which weights and biases contributed to the mistake. And finally, step 4, weight and bias update. It turns those knobs of importance just a tiny bit to reduce the error for the next time around. And exactly how it updates those knobs is through an incredibly cool optimization algorithm called gradient descent. Imagine you're blindfolded on a snowy mountain, and your goal is to reach the absolute bottom, the global minima, where the error is 0. You feel the slope of the ground with your feet, and you take a step downhill. That is exactly what the model is doing mathematically. The slope is the gradient of the error, and the labeled data from our answer key acts as the anchor, constantly cooling the model down the curve toward the lowest possible error. Now, the learning rate controls how big of a step the model takes. If it's too big, it overshoots the bottom entirely. Too small, and it takes forever to learn. To summarize this entire beautiful process, let's look at this quote derived from our sources. Neural networks learn by adjusting their parameters, their weights and biases, to minimize the error between predicted and actual outputs. It is truly amazing when you think about it. It's just a relentless, high-speed process of guessing, checking the answer key, sending the error backward, and tweaking millions of tiny mathematical knobs over and over, until the machine can look at a photo it has never ever seen before and say, with 99% certainty, yep, that is for sure a dog. But I want to leave you with a somewhat provocative thought. As you'll see, the machine is essentially just a mirror. It minimizes errors based entirely on the labeled datasets, the answer key, that we humans provide it. So what actually happens to the AI's real-world accuracy if our labeled data is deeply flawed or just flat-out incorrect? Garbage in literally means garbage out. Understanding the anatomy of classification doesn't just show us how mechanically brilliant these machines are, it shows us how absolutely crucial it is that we provide them with high-quality, accurate, and unbiased data. Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.